discussing ML Systems Conference Part 1. The conference here in Santa Clara is about machine learning systems. So this is hardware all the way up the stack towards the model. And people think about different problems within the stack, whether it's hardware design, model design, and all the things in between. This is, in a nutshell, if you want, almost a question also of what is it that makes NVIDIA so unique and what can be done to enhance the competition within the space. And then also, what are the open problems? Open problems, for example, inference, efficiency on the edge. Those are things where NVIDIA is still reluctant to put big dollars against because the market is supposedly not there yet. Now, we'll see about that. But in general, the conference is very interesting. This first day was about professionals, young professionals looking for academic jobs and industry jobs. So this was not a fully academic day, but nevertheless, some of the invited talks are actually really, really interesting. So I wanna discuss two of those in the first part. One is her name is Azalia Mirhoseini, Stanford. So I'm gonna call it Professor A from Stanford. She was talking about scaling, and then Xupeng Miao from Caltech, he was talking about a model that helps in reducing the memory requirements for training. This is not even on podcast. It's May 13, 2024. This is Krimdelko. For the data fund is up 1.5%. The market's up 20 basis points. For the year, we are down 18.2. The market's up 9.5. We're underperforming by 27.7%. ML Systems Part 1. Again, this is a conference about system, hardware, and the stack as a whole for machine learning. So it's specialized for machine learning because some of the problems are very unique. For example, we have very large memory requirements, I/O requirements for memory, because we're constantly updating weights. We have the problem of training and inference, which are two different types of problems. We have the question of energy consumption, dollars per token. We have questions along the lines of how to efficiently do inference in terms of latency, but then also in terms of power and money. So, for example, the Tesla full self-drive is doing really well with the inference, but you could imagine adding large language models or vision language models to the stack and bring semantics to the mapping, but then you have an inference problem because it takes a long time to first token, for example, or time between tokens, two metrics that sort of measure inference could be problematic if you do this in the car right now. You have to find ways to do this more efficiently. So in that context, I want to introduce the first speaker today, or the first one that I'm talking about, and that would be Professor A. Stanford. And she's talking about scaling. So you can scale across the data, the model, the software, and the hardware. So meaning when you scale, you can think about, okay, we want to do a lot more data. And how do we do that? And one of the problems with a lot more data is to make sure that the data is clean, that the data conforms political issues such as not having racist comments in the data, that kind of thing. But also, more interestingly, actually, one of the problems is harm versus what they call harm versus helpful. And what that means is, if you take a self-driving car, very simple, and you ask yourself, look, I could have the car always be as harmless as possible. Well, in that context, the car would, let's say, just never drive when there is a pedestrian in the vicinity of the car, right? That would be very harmless behavior, but it's not very helpful. So you have to, still drive around, and it would be very helpful if the car keeps driving, but then it could cause some harm. So you can find a middle way, and what Professor A is introducing here is Constitutional AI. It's work that she's done together with other people at Anthropic. And the idea of Constitutional AI is that you train a model with data that comes in, and you first discriminate the data against a set of principles. That's why it's called constitutional AI. So you set a set of principles. By the way, those principles can be learned as well, right? You could, for example, have a model that continuously discriminates for racism. And then you could say, look, we don't want data, we don't want the model to be trained on data that is racist. Now, of course, the conversation immediately starts, well, what is racism? Now, you could learn that too, but I think that's, again, that's a pretty tricky road. And I actually had a little bit of a controversy with her about this, because I feel like this goes against some of the openness and liberty and freedom type of aspects of not just AI, but society in general. So it's very dangerous to go down that route. But on the other hand, there is a problem that needs to be solved, and that is, how do we actually make sure that the models that we train are trained on the kind of data that we want, that it's clean and it's also desirable. So constitutional AI is one of the solutions. But for me, I think it could be very interesting for robotics, because you can use that concept of constitutional AI also for non-political things, right? Constitution doesn't mean it has to be political in the sense, oh, you know, you're not doing something against the law. It could just be, like I said, for example, in the self-driving car example, you could have this concept where you say, look, I want to train on data where the car continuously is very close to pedestrians, but doesn't hit them, doesn't scare them, but just drives around like in a normal way, like say, for example, we would drive around as humans in the traffic. And this is the other thing that I want to introduce here, which is constitutional AI could be very useful for generative AI and generative data, synthetic data generation for training, because you could actually have constitutional AI as part of the stack that generates the data that then can be used for training. So this, to me, is a very interesting avenue, and I think Professor A's ideas are in that context very interesting. And I think this is one of the nice examples of when you go to a conference like this. It's definitely sort of the gold digging type of attitude where you have to turn a lot of stones, and sometimes those stones are not the most interesting ones, but sometimes you find real nuggets. And this, to me, this is definitely one of the nuggets, which is that one of the solutions to in general, to training models at scale with data is to not have to supervise them, and constitutional AI could do that, and also to generate the data. Mixture of experts, gate data to specific expert. Now that, the idea of mixture of experts, we discussed this before. Here, the idea is that you have, what you don't want is, you don't want to have to continuously attend every token to every other token in the model. This would be computationally explosive, right? So what you want to do is you want to bring in data and then guide the data to be processed in parts of the model where it's most useful for that data to be processed in. One thing you can do is you can just say, look, I'm just going to do all the low weights here and all the high weights over there. I'm going to sparse also, meaning when things are almost close to zero, I'm going to just put them to zero. So you could do that. You could have different types of gating mechanisms. I don't want to go into detail, but the idea of mixture of experts, again, is to sort of batch the system. It's related to the tiling concept. Tiling is when you batch the incoming data in training time, but the same applies to inference. Also, you batch it so you have a certain amount of data that can be trained on the SRAM of the GPU, which is very important. That's part of another presentation. Thierry Tambe was here, the flash attention person that I discussed at length at NeurIPS. I think it's one of the highlights of NeurIPS, in my opinion. So he was here. He was talking about the same concept. The idea of flash attention in general is that you have you want to separate the data into batches and then have them be processed on the GPU with the amount of memory available on chip, so you don't have to go I/O. But let's get back to Professor A. She introduces two other papers. One is Hydragen paper, prefix fine-tuning, and the other is CAT, Sparcity. So the way I understand both of these concepts, let's talk about hydrogen. So the idea of hydrogen is that you take in data and then you summarize it under a certain prefix, and then you just process the data with the same prefix, or actually you have data with similar prefix, you get rid of let's say you have, you have 100 units of data and you have 10 prefixes. So that means that there is, and it splits very nicely. So the first 10 are prefix 1, the next 10 are prefix 2, and so on and so forth. All you're going to do is process 10 prefixes. So because the prefixes are similar data points, and therefore you don't have to process all of them. That's the core idea of prefix fine-tuning. The CAT's paper is sparsity. Can we extract more sparsity out of LLMs? So the question is, can we get rid of weights, right? This is one of the biggest endeavors, in my opinion, this whole ML systems community. And that is, look, let's say you have 100 weights and data comes in, and now you want to process each token against each other token in the model and update every weight and every bias that is associated with those tokens. Or can you somehow predetermine and say, look, this data that comes in is only going to affect a small part of the existing data set. The rest we don't even touch. How can we extract more sparsity out of the model? This is absolutely key. This is something NVIDIA is incredibly strong at. This is, according to Bill Daly, Chief Science Officer of NVIDIA, this is the main idea, actually, of the whole, Moore's Law thing with NVIDIA and the extraction of sparsity. Now, how exactly they do it, that's technical, I think, beyond this episode, but I want to just make the bridge to Tesla here, because Musk spoke about this, the necessity to be a leader in inference when it comes to full self-drive. And Tesla is obviously proving it in the pudding. Full self-drive is working amazing on a hardware stack that is definitely, from a cost perspective, absolutely acceptable, because you can buy a car for $50,000 and you have this amazing inference machine with it. So clearly they've done something right there. And whether they must have been using all these models. But I think in general for us, it's important to understand what are the actual ingredients that go into more efficiency when it comes to inference. And one of them is sparsity. That is definitely so gated. So gating and sparsity, which are related. Gating is, okay, which parts of the model do I move on which chip? So I can process it on chip with the memory on chip. I don't have IOs. And the other is sparsity. Which parts of the model do I process and which parts do I disregard? So that's that would be Professor A's presentation. The next presentation is Xupeng Miao from Caltech. He was talking about memory efficient training, scaling parameters, and solving the memory wall. And he presented a paper, it's in the show notes, GaLore, and it's an optimizing to reduce memory requirements. So what's really interesting about his presentation is a statistic that he showed, which is that if you look at the memory requirements of training, storing actual weights is about 20%, 80% is weight gradients. So those are the intermediate weights. And that's something you can work with. And the way you can work with that is GaLore. What GaLore does is the weight gradients, they have a certain characteristic, a certain structure, which is that in a lower dimensionality, they're very similar. Or let me know, like they're very sort of black and white, right? So they cluster they like to cluster. So when you lower the dimensionality of the weight gradients, you get a lot less information. That is, you basically reduce the amount of information. Now, you don't necessarily lose information as far as training is concerned, but you reduce the amount of necessary information to still convey the same message. The way I understand this intuitively is just think about it like you can, this is the concept of having a person, a very complex person, two people, let's say a lady A and a lady B, and one of them lives in New York City and the other lives in Minnesota. And you can capture those two ladies with zip code and education and maybe age. You know everything about this person you need to know. So you can reduce the amount of necessary information to get the result, which is maybe to make a recommendation where this lady should go on vacation next time. So the same thing applies in this general training approach to large language models, and that's what was discussed in this presentation. So we have this concept again of weight gradients that can be reduced. GaLore actually there's low rank in the name, something like there's LoRa, which is low rank matrix for fine tuning, but doesn't work for training. Well, this GaLore, which is an adaptation of LoRa to training, where you use gradient weights and you low rank them and sort of combine them, and you use that to predict where to train. So you have this big space of possible attention tokens attending each other, and you reduce that to just where there is the most extractable information in the training set. That's the idea of GaLore. There's a quote from the paper: "Subspace learning recent studies have demonstrated that the learning primarily occurs within a significantly low-dimensional parameter subspace." This is key: significantly low-dimensional parameter subspace. So you don't need to attend every token to everything. You can reduce the amount of training and memory requirements and still keep the same performance. So to summarize the first two presentations of MLSys, one is Professor A from Stanford. She was talking about scaling and how to scale data and model and hardware and software. She was introducing ideas like Constitutional AI, mixture of experts, prefix fine-tuning, and sparsity identification. And then Xupeng Miao from Caltech talking about GaLore, which is a low-rank matrix approach towards training, where you reduce the amount of memory required for weight matrices by finding low-rank subspaces that are still have enough information to have high-performance training, but require a lot less memory for training. I think the last word I want to say about this is maybe just for new listeners, why are we at this conference? What is the purpose of this for Orange Capital Partners? We're invested in AI. It's a big deal for us. All our money is invested in it, so it's useful to know where the industry is going. And this is actually kind of a recruiting / latest in academia type conference. So the ideas from here, they will translate into industry pretty fast. And there's some real applications, for example, for inference efficiency and training efficiency. And we are exposed to both of them with NVIDIA and with Tesla. Thank you.